So today we will be going through some context-free grammars for programming language constructs. So what we did last time is that we reviewed context-free grammars, the concept of context-free grammars, and we went through a few examples using the basic alphabet A-B. Today we will be writing context-free grammars for actual programming language constructs. Using the alphabet. Our alphabet for today is going to be what? So we mentioned this last time. So what will the alphabet? No.
Things like
no. It will be the output of the scanner, right?
Yeah.
So it will be the whatever the scanner recognizes. So the identifier or a variable name or a function name will be considered one symbol in our alphabet at the parsing level. At the parser level, the identifier will be considered one symbol, and the number will be considered one symbol. Something like if is one symbol, else is one symbol, etc. But for the operators, the single character operators like plus or minus or multiply. So each one of these will be considered. It will be considered a symbol in the alphabet at the parser level. So this is a syntactic category by itself. The plus is a syntactic category that includes only one symbol, which is the plus symbol. Remember, the NFA for these had only one branch for this that recognizes only this operator. Okay, so now what if we write an assignment statement like x12 equals ABC plus DFG, DEF. Okay. So now in this case, this is an assignment statement. So if we try to write a rule for this, we have on the left-hand side, we have an identifier. And here we have the assignment operator. Then we have another identifier plus another identifier. So we can write a rule like this. Assignment. For the assignment is an identifier equals, let's call it expression. In fact, today's lecture is going to be focused on expressions, grammars for an expression with the semicolon. So in this case, this is our expression. So it's identifier equals expression. Now what's the rule for expression? And remember, these words in uppercase, these are the variables, the non-terminals. Assign is a non-terminal. Expression is a non-terminal. Identifier is a terminal or a symbol in the alphabet at the parsing level. So this expression, let's do our first attempt, is identifier plus identifier. So this is an expression, identifier plus identifier. Well, this is going to be enough for this example, right? So this will, this example can be derived from this grammar easily, right? So in this case, we have an assignment. Then our assignment is an identifier, which is the x12 equals expression, and our expression is identifier plus identifier. And in this example, the first identifier is ABC, and the second identifier is DEF. OK, so this will parse very well. But obviously, this is not general enough, right? Why not? Yeah.
Subtraction, division, and multiplication aren't included.
OK, so we can do this easily. I can do subtraction and division and all other operations easily. I can change this from plus to up. And then let me put some space in there. Up identifier. And then my up is plus or minus or multiply or divide. Okay. So now I generalized it to support multiple operators or multiple arithmetic operations in the expression. So now this is more general than limiting this to the add, but it's not general enough, right? Yeah.
Exponents, other operations that use the math dot, like square root and whatnot, count as expressions too.
OK, so remember, those will be function calls. So if you are using extensions that are function calls, so a function call has a different syntax. Now we are looking at the basic expressions that use the built-in operations, the built-in arithmetic operations. We will do parentheses towards the end of this lecture. So for now, yeah, let's, yeah, yes?
It doesn't support more complex expressions if
yeah.
you do more addition or subtraction or whatever.
Yeah, exactly. So here we are assuming that we only have one operation. So, let's try to generalize it. Let's try to generalize the expression by trying this. So let our expression be, let's get rid of this. Let our expression be, for example, expression op identifier. OK. So if our expression is expression op identifier, by the way, is this rule sufficient?
If you just had an identifier by itself.
Yeah, exactly. Generally speaking, if you have a recursive rule, a rule that has recursion in it, it will never be enough for generating actual strings. You have to have a non-recursive definition, a non-recursive production. So remember, you can't have only one recursive definition of expression. You have to have a non-recursive definition, which could be in this case identifier. Not having a non-recursive definition is like having a recursive function with no base. So you have to have a base. Otherwise, recursion will never end. OK, so this is like the base of the recursion. OK, so now let's see if we can use this to parse something like x equals a plus b minus c. OK, so let's focus on the expression part, by the way. Let's focus on this, because we know that we can do the assignment. So we'll do it anyway. So it's assignment. And in this case, we are assigning an identifier to an expression. And our expression in this case is going to be with recursion. So this is going to be an expression. So this is the big expression that consists of an expression minus c. So it's going to be expression minus or in fact, we don't have a minus. I mean, let's do the right thing. So expression op identifier. So we substituted expression op identifier for expression. Then we substitute for this expression another expression op identifier. And what else?
The expression goes to an identifier.
Yeah, expression goes to an identifier. And this op goes to what? Plus. And this op goes to minus. And this identifier, just let's label them. So this is going to be the x. I think I should erase this since we are done with this. So we are now doing this example. Yeah. So
That's A, not X.
so sorry. Yeah. So this is okay. So this is the x. This is the A. This is the B, and this is the C. So this parses very well. This expression parses very well. Now, about this. What if x equals A plus B times C? Now, what if we try to parse x equals A plus B times C with this, using this grammar? So in this case, x is x. Our first operator is going to be, in fact, it will continue to be plus. And our second operator is going to be multiply, right? OK. So now this is the derivation of this. So this parses very well. But do you see a problem here?
The addition happens before the multiplication.
By the way, why are you assuming that the addition happens before the multiplication?
Lower on the tree.
Yeah, so given the structure of the tree, remember that our objective is to produce that abstract syntax tree, right? This is the objective of parsing, to produce that abstract syntax tree. And in this case, with this abstract syntax tree, this is saying that we first add A and B, and then we multiply the result by C, which is not what precedence rules will lead to here. So the precedence, the mathematical precedence rules that we are familiar with would require multiplying B and C and then adding the result to A, right? So this parse tree does not capture precedence, does not capture precedence rules. Okay, so because of this, let's try to come up with a grammar that will capture the precedence rules and that will parse this. Again, let's get rid of the one that we are done with. A grammar that will parse this properly. In fact, this is not going to be hard. So the idea here is the following. So let me write AX equals A plus B times C. So in order to do this, I have to introduce the notion of the mathematical terms. In mathematics, A is added to B times C. So mathematically, what do we call this? What's the mathematical term for B times C?
Product.
What's that?
Product.
Product? No, B times C, this whole thing, this whole piece, B times C.
No, binomial. The term binomial.
No, it's
An expression.
So we call this plus connects two terms, right? In math, we call this a term,
Yeah.
and this is another term.
That's right.
And a term, so these are mathematical terms, okay? Within each term, we can have multiple what? So the B and the C within this term. So this term has only one? No. So what can we have within a term?
Expression.
Identity.
No, this whole thing is an expression. So this is a basic math terminology. So I guess by studying computer science for a long time, you forget the basic mathematical terms. Your brain gets washed with operators and source operand and the destination operand and all of these computer science terms, and you forget the math. So in math, this is a factor, right? So this is a factor and this is another factor.
Yeah, I remember that. It's coming out of CSC 135.
Okay, so the point is that the plus or the minus, it relates two terms, and within each term, you can have a number of factors. Now, this is the key idea. The idea is that the term is a higher level construct that can have within it factors. So this will allow us to write the grammar for expression as follows. Expression is expression plus term
Shouldn't be plus minus, but
or expression minus term or expression. Or, sorry, can I say expression here? If I say expression, then it will be a recursive definition without a base, right? So I have to have a base. I have to have a non-recursive definition or term. Now the term in turn, it's the same thing as the expression, but the relation between a term and a factor is the same as the relation between an expression and a term, except that the operators are going to be multiply and divide. So it's going to be term what times factor or term divided by factor or factor. Yes. And is this definition complete? Is this grammar complete?
no.
No, it doesn't tell me what a factor is. So a factor is
Can be either a number or an identifier.
exactly. So it can be an identifier or a number. Okay. So now let's do a derivation for this. X equals, let's do the derivation here. Okay. So now we have, the assignment part is easy. So it's an assignment. Then we have the identifier equals expression. And this expression is an expression plus term. Then this expression is
Well, first expression goes to an identifier.
so it's an expression plus term. So which one is the expression? So let's so in fact at the top level we have this is our expression and this is our term. So our expression is an expression plus term, where this expression consists of a single term, and this term consists of a single factor, and this factor is an identifier, which is in this case the A. By the way, this identifier is the X. So this is expression plus term. Now this term is what? This term consists of how many factors? 2 factors. So which rule should we use here? Term multiplied by factor. Multiplied by factor. And the first term is going to be what? A single factor. So by the way, don't skip any steps in the derivation or in the substitution. A common mistake that I see in exams is skipping from term going all the way to identifier. So this term, yes, is an identifier, but there is no rule that says that a term can be an identifier. A term can be a factor, and a factor can be an identifier. And this identifier is what? It's the B. Then this is multiplied by another factor, and this other factor is an identifier. And this identifier is the C. By the way, here we are not, the A is not something that is derived from an identifier. The A is just the lexeme that corresponds to this identifier. So this here, it's not part of the derivation. We're just saying that this identifier, this is the actual lexeme for this particular syntactic category. Okay. All right. So this is the this is the derivation of this assignment. Oh, we forgot the semicolon, but it's not a big deal. So it's semicolon, and we have expression and semicolon. In fact, we will focus on the expression, and then for most of this discussion, we will we will forget about we will ignore the assignment and the semicolon. We'll focus on the expression because that's straightforward. That part is straightforward here. Okay, so the interesting part is the expression. Okay, any questions on this? Okay, now the next step is accounting for parentheses. So expressions can have parentheses. Yes?
Are we going to account for exponents or no?
Exponents?
Yeah.
No, not at this point.
Okay.
Yeah. So it's yeah. So let's focus on these binary operators, binary arithmetic operators that are built in most languages at this point. Yeah. So now, what about parentheses? So in terms of precedence, do parentheses have higher precedence or lower precedence than
Higher.
higher? They have higher precedence. So they should be accounted for up top or at the bottom?
Bottom.
No, at the bottom. See, if higher precedence goes more to the bottom. Lower precedence is has a higher level in the hierarchy. So the add and the subtract, they have lower precedence, so they appear higher in the hierarchy. This means that the parentheses, which have higher precedence, should appear even below the multiply and divide in the hierarchy. Okay, so when you go down in the hierarchy, you go to higher precedence because that's what you want to evaluate first.
Right.
Higher precedence is what you want to evaluate first, so it's at a lower level in the hierarchy that is represented by this tree. So in this case, we can, in fact, we can think of if we put parentheses like this, A plus B times C minus D. You have something like this, A plus B times C minus D. Now, in this case, the A plus B is part of this term. So it belongs to this term. And it's in fact another factor that is multiplied by the C. So this term consists of two factors. This is one factor. And this is another factor that are multiplied. Right. So the parenthesis structure is a factor. So where will it fit in this grammar?
Right, in the back.
Yeah. So it's another alternative for the factor. So the factor could be an individual, a single identifier or a single number or parentheses. Whatever is inside those parentheses is going to be. But what should we put inside?
Expression.
Expression, yes.
This.
Yeah, so inside we put an expression. Okay, so let's take an example, see how we can derive something, how we can derive this. I think we'll need more space. Okay, so now let's try to derive this. So deriving this, we have, it's an assignment, and the assignment has a, okay, so it has a, because I need more room for the expression, so it's going to be, let's just show the expression part, because we need all the space for the expression part, which is this. Okay, so let's just derive the expression. So the expression in this case is
Starts with a parenthesis.
Minus term.
expression minus term. Yeah, so this is the first step in the derivation. So it's expression minus term. And this expression consists of how many terms? So this is the, yeah, so this is then an expression that consists of how many terms?
One.
One term, which is this. So this expression consists of a single term. And this single term consists of how many factors? Two factors. So it's term times factor. The left-hand side term consists of, so the left-hand side is this factor, right? So this is a factor. What's this factor?
The parentheses expression.
Yeah, it's the expression. So let me. This factor is parentheses expression. So these are terminals, open parentheses, close parentheses. These are terminals. But the expression is a non-terminal. So now what does this expression? Now for this expression, I will start substituting from the top, right? So I need to find a rule for this expression. And this expression is?
Expression plus term.
Yeah, expression plus term. And this expression is?
Just term and then factor.
Yeah, exactly. Term, then factor, and this factor is?
The
Identifier. Identifier, and this identifier is A. Okay. Now this term is a factor, and the factor is an identifier, and this identifier is
B.
B. Okay. Is everyone following this? Okay. Now this factor,
Just another identifier.
so it's an identifier, and this identifier is C, and this term is a single factor, and this factor is an identifier, which is D. Okay, so this is going to be our, what we call the classic expression grammar. So this is the classic expression grammar. Oh, in fact, yeah. Well, classic expression grammar does not include the assignment. So this would be a classic assignment grammar with the assignment. So, but this is the, the grammar for an expression. Okay. So, and this is the grammar that we will be using for expressions. We will be doing a lot of work on expressions. Of course, this doesn't tell us how to build a parser, right? Because in order to build a parser, what do we need to do? So suppose that you have a language, and this language only has expressions. It doesn't have anything else. And you would like to build a parser for this. So what do you need to do? So we did this derivation. Yeah.
You need to build this abstract syntax tree?
Yeah, but how? So when we did this derivation tree or parse tree, so this is what we call, derivation tree or parse tree. We did this by inspection. So we looked at the grammar, and we looked at the actual string that we are trying to parse, and we tried to do some kind of matching. And we succeeded here because it's this string is very small, and we did this by inspection. So in order to get this figured out, maybe you tried in your head, maybe you tried a couple of possible solutions or possible substitutions. For example, maybe you tried plus here, but then you figured out, no, this is not going to work. And when you were looking for the right derivation or the right substitutions, you were looking at the whole string, right? So in order to, for example, how did we know that the first substitution up top, the first substitution that we make, is expression minus term, not expression plus term? We knew this because we looked at this, right? We looked at this whole string, and we found a minus here. And we said, OK, so this is going to be one expression, and this is going to be a term. So in fact, in this case, in order to come up with this derivation by inspection, we had to look ahead like how many? 5, 6 symbols. 1, 2, 3, 4, 5, 6, 7, 8. So we had to look at symbol number 8 in order to figure out the right derivation. And in fact, compilers do not afford looking 6 symbols ahead. In fact, all the parsing algorithms that we will be learning will have only 1 symbol look ahead. So they determine the right substitution, the right step in the derivation by only looking 1 symbol ahead. So they will only look at this or this, the first symbol, and based on that they will decide. So in order to come up with such a parser, the grammar has to be structured in a way that supports this, that supports deciding or figuring out the right substitution very early by only one symbol look ahead. Okay, so today we will just try to identify the possible the problems and complexities with building a parser. A parser is just a program that does this, automating what we have just done on the board by inspection. A program that does this automatically and knows what substitution to make. So let's look at this classic expression grammar, and let's try to parse A plus B minus C. Okay, so now we know how to do this derivation. Now let's try to build a parser for this. Okay, so the parser, and for now, our language only has expressions. It doesn't have anything else. We're focusing on expressions. So our parser is trying to decide whether this is a valid expression, and if it's a valid expression, it needs to construct the parse tree for this expression. So, okay, so one way of doing this, let's try to do this. It will say, okay, the start variable is expression. What should I substitute for expression? In fact, if we are building a parser that does this systematically, it's going to go, okay, I will try the first substitution. Because right now, this parser sees this A. So it will say, okay, I'm going to say expression plus term. This is my first substitution. So I did one step in the derivation. Then the next step, if we are going to do leftmost derivation, so if we are doing leftmost derivation, now we should be looking for a substitution for expression or term. Expression, because that's the leftmost non-terminal. So for expression, I'm going to look for a substitution. But in fact, if we are going to do this systematically, then we are going to substitute expression plus term again. And if we keep doing this systematically, remember that now we are looking for a program, an algorithm for doing this. If we keep doing this systematically, it's going to keep doing expression plus term. Expression plus term forever.
Yeah.
So the point here is that if you do leftmost derivation and you have left recursion in your grammars, then you will be substituting forever. So you will be in an infinite loop. So leftmost derivation and left recursion don't go, don't work well with together. So in this case, you will keep substituting forever. Now let's say that, okay, we figured out a way. By the way, this is not how the parsers that we will, this is not one of the parsing algorithms that we will be learning. We're just trying to understand the problems and complexities with parsing. So let's say we figured out how to get rid of this, infinite recursion or endless substitution, and okay, we will do expression plus term. Now, with expression plus term, and the second time we will substitute something else, like expression minus term. To avoid going into an infinite loop, and then at this level we substitute for expression term. So will this lead to a correct parsing? No, it will not. So in this case, even if you finish this with the identifier, this will lead to the A, and this will lead to the B. It's not actual, and this will lead to the C eventually. So this will not lead to the right parsing. Now, if we continue with this, okay, we'll say, okay, we did all of these substitutions and we didn't reach a valid parse. This doesn't mean that the input string is invalid, because maybe one of our choices or decisions or substitutions was wrong. So let's backtrack and try something else. So we backtrack maybe here, instead of substituting. Well, we backtrack to this term. We try all possibilities, and none of them is going to work here. So whatever you substitute here, it's not going to work, because you have already made some wrong decision at the top. So the idea is that if you make a wrong decision at the top, everything that is based on that will be wrong. But in order to identify where the wrong substitution is, you will have to do a lot of backtracking. So you try this, nothing works here, so you go back to this. Expression minus term doesn't work. I try expression plus term here. Expression plus term doesn't work either. So let me try term. Will term work? No, term doesn't work. So I'm going to backtrack all the way to the first substitution that I made. And now, okay, I tried everything that is based on expression plus term. I tried all the possibilities, down tree based on expression plus term, but none of them worked. Then there must be something wrong with this, if the input string is valid. So I'm going to try something else. I'm going to try expression minus term. And when I try expression minus term, again, at this level, I have to try all the different possibilities. Of course, here, so I can, for this expression, I should try expression plus term, expression minus term, and term. And in this case, which one of them is going to work? Yeah, expression plus term. Okay, and expression plus term here is going to lead to the right derivation. So the point here is that if the parser, if an actual parser does all of this, it makes substitutions, then when it gets to the point where it cannot find the correct derivation, it backtracks to the upper level, and then it tries all possibilities at that upper level. And if none of them work, it's going to go to the upper level, and it keeps backtracking and going up until it goes to the top level, and it will try something else. So this kind of backtracking obviously will not lead to an efficient parser. So with this backtracking, basically we are traversing a whole tree. And when we are traversing a whole tree, the number of nodes in a tree is in general an exponential function of the depth of the tree. So if we are going to do this exponential type of trying all possibilities and all substitutions, this is not going to lead to an efficient parser. So we want a different approach, to take a different approach to parsing. that will allow us to figure out the correct substitution at the up top from the very beginning, and based on only one character look ahead. For this particular grammar, there is such an algorithm, and this algorithm will be based on eliminating left recursion. So if you eliminate left recursion, you can find a parser. You can find a parsing algorithm that will not have to backtrack. It will always be able to determine the right substitution at each step in the derivation by only looking one symbol ahead, not 2 or 3 or 4. Only one symbol ahead. It will determine what the right substitution is. So what's left recursion elimination? Left recursion elimination is restructuring this grammar such that we don't have left recursion, we have right recursion. So let's try in the remaining minutes to see the idea. So if I have something like x equals x alpha or beta, this is a grammar with left recursion. So if I do some derivation here based on this, x is x alpha. I keep substituting x alpha, x alpha, x alpha. And then to end this derivation, the final substitution for x has to be what? Beta. So what does this mean? It means that when you have left recursion here, this will generate a beta followed by as many alphas as you want. Right? So this is what this generates. Beta followed by as many alphas as you want. And this can be written in the following equivalent format. So there is a beta. I know that the beta will be to the left. The leftmost symbol has to be a beta based on this. So it's a beta followed by as many alphas as I want. So let's put this in another variable that we call x prime, where x prime is
alpha or x prime.
Yes, alpha x prime or alpha. Well, here you are requiring at least one alpha, but we don't have epsilon. Yeah. So this is the equivalent right recursive form of this. So this is left recursive. And this is an equivalent right recursive form. So these two forms are equivalent. It turns out that for the kind of parsing that we are about to study, or that we will be studying next lecture, the right recursive form works very well, and it will allow us to parse any string that belongs to this language by only one symbol look ahead. So we'll do that next time, but before we end this lecture, are there any questions on the equivalence between this left recursive form and this right recursive form? Is everyone convinced that these are equivalent? Just based on this, do this derivation and see that this will keep giving you alphas, but the leftmost is going to be a beta, because at the end you have to substitute a beta for x. This is the base case. This is your base, and this is your recursive part of the definition. Okay, so next time we will see how this right recursive, we will write the right recursive form of this, and we'll see how it will make parsing much more efficient. Questions? Okay, so I'll see you on Friday.